Today, I want to shine light on a critical global health problem, respiratory viruses, often overlooked yet responsible for hundreds of thousands of deaths each year, and how a molecule called Neuregulin-1 might help change the way we protect the lungs from them. But first, a little bit about me. Hi, I'm Sophia. I'm from Columbus, Georgia, and a rising junior at Columbus High School. In school, I'm heavily involved in robotics, student council, science Olympiad, Cancer Kids First, and RISE, a youth leadership initiative. I'm passionate about molecular and cellular biology, but I also have a deep interest in ecology. I chose this topic due to my involvement in research in biology and pathology through various research projects. Outside of academics, I've been playing piano for over 10 years and enjoy swimming for fun. Respiratory viruses are among the world's deadliest pathogens. Lower respiratory infections remain the fifth leading cause of death globally, contributing to over 2 million deaths annually, particularly affecting children under 5 and older adults in low-resource settings. Respiratory syncytial virus, or RSV, alone is responsible for more than 200,000 deaths in children under 5 each year, while influenza contributes millions of hospitalizations around the world. Our current tools, like vaccines and antiviral medications, are largely strain-specific, expensive, and difficult to distribute at scale. That leaves enormous gaps in protection, especially during seasonal surges and outbreaks. So what causes respiratory infections? Fatal respiratory infections results primarily not from viral replication, but from collapse of the lung's epithelial barrier. When viruses invade, they damage the tightly packed epithelial cells lining the airways. This damage causes fluid and proteins to flood the alveolar spaces, severely impairing gas exchange. On top of that, an overactive immune response releases cytokines and proteases that worsen tissue injury, turning a localized infection into systematic respiratory failure. So protecting the epithelial barrier became a key part of my focus. Cell death and inflammation play a key role in how viral infections damage the lung. So our hypothesis is that if we can shift dying cells from necroptosis to apoptosis, we might reduce inflammation and protect the lung barrier. So how does this actually work? One pathway is necroptosis. When triggered, it causes the cell to burst. This releases danger signals that lead to inflammation and more tissue damage. On the other hand, apoptosis is a controlled, non-inflammatory form of cell death. It involves caspase-3, which causes the cell to shrink and be safely cleared without triggering inflammation. That led to a key idea in the research. So our research began with a surprising observation in prior studies that mice sensitized to house dust mite extract, essentially mimicking an allergic state, exhibited near complete survival, following otherwise lethal doses of Sendai virus, which serves as a mouse model for human RSV. And when we looked at their viral loads at peak infection, they were actually lower than those in non-atopic mice. This led us to believe that something about the atopic state itself, beyond just immune activation, was offering protection. Using RNA sequencing of lung CD11c positive immune cells from atopic versus non-atopic mice, we identified Neuregulin-1 as one of the most upregulated transcripts in the atopic group. Neuregulin-1 is part of the epidermal growth factor family and plays a role in protecting cell survival, growth, and tissue repair. This profile made NRG1 our top candidate for lung barrier protection. Next, to evaluate whether NRG1's protective capabilities in isolation, we administered recombinant NRG1 intranasally to mice for 5 days, followed by infection with the lethal dose of Sendai virus, or SEV, or mouse-adapted influenza A virus. At 500 nanograms per dose, daily treatment resulted in over 75% survival, compared to nearly 0% in the control group. This dramatic increase demonstrated that NRG1 alone is sufficient to confer substantial protection against fatal respiratory viral challenge. To understand how Neuregulin-1 actually protects the lungs, we looked at two key mechanisms: preserving the epithelial barrier and shifting the way cells die during infection. While I won't go into detail, the results show that in NRG1 treated mice, we saw over 60% less dye in the bronchoalveolar lavage fluid, or BAL, compared to controls. That tells us that NRG1 helps seal the barrier and reduce the fluid leakage that leads to respiratory failure. Results also show a twofold increase in caspase-3 activity, which marks non-inflammatory apoptosis. So not only does NRG1 tightly tighten the barrier, it also shifts cells away from destructive inflammatory death and towards a cleaner, controlled process. To see if these protective effects translated to human cells, we tested NRG1 on primary human epithelial cells grown at the air-liquid interface, which closely mimics the human airway. Basolateral administration of NRG1 5 days pre-infection led to a 50 to 70% reduction in viral spread, which we measured by a drop in green fluorescent protein signal from RSV-infected cells. To close out the experimental findings, we also looked at the structure of the airway tissue after NRG1 treatment. Histological cross-sections showed that the epithelial layer became thicker and more organized, a sign of enhanced repair. This type of issue remodeling suggests the barrier isn't just being protected, it's actively being rebuilt. Together with the viral reduction, this points to NRG1 not only limiting damage, but also helping restore lung integrity. And with that, we arrive at the bigger picture. Respiratory viruses remain a major global threat, especially for vulnerable groups. What makes Neuregulin-1 unique is that it doesn't target the virus, it protects the lungs. It straightens the epithelial barrier and shifts inflammatory cell death towards a safer, controlled process. Across both mouse and human models, NRG1 reduced airway leak and preserved lung integrity. These results point to a promising host-directed strategy that could offer broad protection without relying on virus-specific treatments. Now, I'd like to thank Dr. Rule for guiding me through analyzing this research for the ongoing research. And I'd love to thank the Global Health Leaders Conference for this amazing opportunity, and also you, the audience, for listening. Thank you so much, and if you have any questions, please reach out to me via email, and I'll be more than happy to respond. Thank you.